Alright, in this video we're going to talk about Gay-Lussac's law. In Gay-Lussac's law, in the first video you just learned the everyday applications of Gay-Lussac's law, so we're going to learn how to practice working them. You just got the formula P1 over T1 equals P2 over T2. Quick question, what's constant for this law? Well, it's the only thing that's not in it, and that means volume is constant. It's not in the formula at all. So the volume changed the same. The volume changed. Pressure changes, temperature changes, but volume is constant. Constant means it does not change in this formula. So if you're ever asked what's constant for a law, whatever's not in the formula is constant. Now what we're going to do is we're going to practice a problem, but a couple of quick reminders. This is basically like a mix of Boyle's law where you deal with pressures and Charles's law where you deal with temperatures. Pressures have to match, P1 and P2 have to match, and T1 and T2 have to be in Kelvin. Got to remember that. It's got to be in Kelvin in order to work the problem. It has to be a scale that can never be negative. Okay, so let's try a problem and see how we do. A gas has a pressure of 1.6 atmospheres at 20 degrees Celsius. If its pressure, and I hope you're doing this one with me, changes to 200 kPa, what is temperature 2 in degrees Celsius? Now, if you'll pause the video for a second and make sure everybody has a chance to write it down, then we'll work it together. I'll be right back. Alright, let's work the problem. The gas has a pressure of 1.6 atmospheres. You'll notice I'm just writing it where it goes. Reminder, pick the formula, plug the numbers where they go. When you have a test coming up, you need to know which law to use and how to plug into it. So always start with the formula and plug the numbers in. It says that it's at 20 degrees Celsius. That should kick off an alarm in your head. That's not in the right units. You're going to have to fix that. Pressure is going to change to 200 kilopascals, which also is a problem. We're going to have to fix that. There's my X. They want the temperature in degrees Celsius, so we're going to have to work around that. So let's see what we do. I'm going to go ahead and take the problem out. First thing is my pressures don't match. So I need to either change atmospheres to kilopascals or kilopascals to atmospheres. It doesn't matter. So I'm going to go ahead and take 1.6 atmospheres, and I'm going to railroad track it. Atmospheres, so it cancels. 1 is with atmospheres. kPa is 101.3. That's the same numbers we were doing when we were doing Boyle's law. And so I want to take my calculator and calculate the answer. 1.6 times 101.3, and I get an answer. You can see it on the screen. 162.08. 162.08 kPa. So that means I'm going to mark this number out, and I'm going to write in 162.08 kPa. So now I have that value written in there, so the pressures now match, so I can work the problem. Now there becomes another problem really quick, is my temperatures are supposed to be in Kelvin. And they're not in Kelvin. Sorry about that bell going off. It's not in Kelvin, so I'm going to have to work that problem as well. Well, I'm going to take 20 degrees Celsius, I'm going to add 273.15, and so that's 293.15 Kelvin. Pressures are matching, and temperatures in Kelvin. That means when I work the problem in a second, the answer is going to come out in Kelvin. It asks for Celsius, but I can only work it in Kelvin. Remember, work it in Kelvin. Now, to solve this problem, I'm going to cross multiply. So that means I'm going to get 162.08 times x, and that's going to equal 293.15 times 200. That number is 58630. And so I'm going to divide by 162.08, so I can solve for x. And 162.08, simple algebra 1 skills. So I'm going to divide by 162.08, and I get an answer of 361.73 Kelvin. How do I know Kelvin? It has to match. Question wants Celsius, so I'm going to subtract 273.15. So when I subtract 273.15, I get 88.6, I'm just taking it to one decimal place, 88.6 degrees Celsius. And that's my answer. I'll move that up so everybody can see it. 88.6 degrees Celsius when I work the problem out. And so I made my pressures match. I made my temperatures Kelvin. I solved. I got an answer in Kelvin. The question wanted Celsius, so I subtracted 273.15, and I get the answer in Celsius. So when I'm working the problem, I have to put everything in the units that are proper. This is just like Boyle's Law, have to match, so I did that. By railroad tracking, I could have changed either one, but I want them to match. Temperature has to be in Kelvin. And so really, Gay-Lussac's law is really a mix of Boyle's and Charles's law. The skills you learn in both, you just use them. Now, quick hint. You're going to see some problems along the way. Let's just pretend that this came out 261. This is the wrong math. But let's say that the answer was 261.73. Let's say that would have been our answer, 261.73. And I have to subtract 273.15. If sometimes you're going to get negative Celsius. Don't let that trip you. Can you have negative Celsius? Absolutely you can. It can be negative. What can't be negative is Kelvin. That's why we calculate in Kelvin. So there's no way we get negative pressures, negative temperatures, negative volumes. If you subtract by 273.15 and you're going back to a Celsius unit like you are here, and you get a negative Celsius, that is appropriate. You can have negative Celsius. You just can't have negative Kelvin. Now, this problem didn't come out with a 2 there. It was really a 3. So we ended up getting an answer of 88.6. But if you ever get a negative like this one, you know you're doing it right because you can have negative Celsius. Now, you're going to get to practice some Gay-Lussac's problems. Good luck. I know you're doing a good job. Keep up the good work. In a few days, you're going to be having another test. Talk to you later.